Small gas engine construction and operation. This video will explain the construction and operation of typical small gas engines. It will identify and summarize the major components of both two-stroke and four-stroke cycle engines. This information will help you understand how engines are supposed to work so you can repair them when they fail to operate normally. Most small gas engines are termed reciprocating piston engines because they have a piston that slides back and forth. The power for engine operation is generated by burning a fuel, usually gasoline. Note the major parts of a basic piston engine. The fuel is burned inside the combustion chamber. The resulting gas pressure pushes down on the piston and connecting rod. The resulting piston movement spins the crankshaft, which is mounted on main bearings. A heavy flywheel keeps the crankshaft turning smoothly. Piston rings are used to prevent pressure leakage between the piston and cylinder wall. They also help scrape excess oil off of the cylinder, causing it to return to the bottom of the crankcase. The lower end of the connecting rod mounts around the crankshaft rod journal, and the other end fits around a pin inside the piston. This allows the connecting rod to swing around with the crankshaft while also moving back and forth inside the piston. These parts work together to convert the piston's reciprocating motion into more usable rotary motion at the crankshaft. To allow the flow of air and fuel into the engine and burn gases out, a valve train is often used. Basically, when the cam lobe moves into the lifter pushes the valve open. The valve moves off its seat and opens the passages into or out of the combustion chamber of the engine. In a four-stroke engine, 4 events complete one cycle: the intake stroke, the compression stroke, the power stroke, and the exhaust stroke. During intake, the piston slides down to pull the fuel mixture into the cylinder. During compression, the piston slides up with both valves closed to squeeze the mixture. On the power stroke, the mixture burns and forces the piston down. On the exhaust stroke, the burned gases are pushed out by the upward moving piston. During actual engine operation, these 4 strokes happen more rapidly. Remember, on the intake stroke, the intake valve opens so that mixture can be pulled into the cylinder. On the compression stroke, both valves are closed and the mixture is compressed to ready it for combustion. On the power stroke, the spark plug fires to make the fuel mixture burn and expand, and on the exhaust stroke, the piston slides up and the exhaust valve is opened to purge the burned gases from the engine. Discussed later, a 4-stroke cycle engine also has many other components to support its operation. A 2-stroke cycle engine, as implied, produces power on every 2 piston movements. It also has oil mixed with its fuel. A transfer port through the side of the cylinder wall allows an air, fuel, and oil mixture to be pulled into the engine combustion chamber when the piston slides down. As the piston moves up, it covers the ports to seal off the combustion chamber. The piston continues to slide up and compresses the mixture to ready it for combustion. The spark plug then fires near the top of the piston stroke. The mixture burns and expands to force the piston down. When the piston uncovers the exhaust ports, the burned gases rush out of the engine, while at the same time a fresh air, fuel, and oil charge flows into the cylinder from the other side. The inward flow of the fresh charge through the transfer port also helps push burn gases out. A reed valve is often mounted in the intake port to only allow flow in one direction into the crankcase. In this illustration, the reed valve is at the bottom of the crankcase immediately after the carburetor. The reed is opened by crankcase vacuum to allow a fresh charge of air, fuel, and oil into the crankcase. The vacuum is formed in the crankcase every time the piston slides up. When the piston slides down, pressure is formed in the crankcase. This causes the reed valve to close and the charge to flow up through the transfer port and into the combustion chamber. Here is a cutaway of an actual reed valve. It is simply a spring steel one-way valve. With higher pressure on one side of the reed flexes open to allow flow. However, when pressure develops on the other side or in the crankcase, the reed valve closes to prevent reverse flow. A reed valve stop prevents overflexing and damage to the thin reed. Now that you've reviewed the basic parts and operation of both 2- and 4-stroke cycle engines, you're ready to learn about other support systems on typical small gas engines. Gravity feed is often used to push liquid gasoline from the tank to the carburetor. A fuel filter is normally used between the tank and carburetor to prevent any debris from entering the carburetor. Just as a lighter burns its vaporizing fuel slowly, liquid fuel will not vaporize and burn quickly enough to keep an engine running. However, if you atomize the fuel into tiny droplets, the fuel will vaporize, flash, and burn much more quickly. This more violent burning is needed to support combustion and engine operation. When air flows through a carburetor, it pulls liquid fuel out of the bowl and nozzle. Liquid fuel breaks into tiny droplets and mixes with the air entering the engine. The venturi, or restriction inside the carburetor body, produces a vacuum that pulls the fuel out of the bowl. The float keeps the fuel bowl full by opening and closing a needle valve. The choke at the inlet of the carburetor can be closed to aid cold engine starting by richening the mixture. The throttle can be opened and closed to regulate the engine's speed and power. The carburetor throttle lever and choke lever are connected to the operator's hand controls. Here you can see the choke at the inlet of a carburetor. When it is closed, the engine is starved for air. More vacuum is produced at the nozzle and more fuel is pulled into the engine to support combustion when parts are cold. An air cleaner is normally mounted over the inlet of the carburetor. It is used to filter out debris that could wear and damage internal engine parts. Many small gas engines use a separate air cleaner element that fits in a metal housing or cover. A foam rubber wrapper can also be used around the paper element to increase filtering efficiency. A governor is used on small gas engines to protect the engine from overspeed damage and to maintain engine speed with load changes. It closes the carburetor throttle valve when a preset RPM is reached. With an air vane governor, an air flap or vane is positioned next to the cooling fins on the flywheel. As the flywheel spins more quickly, increased airflow acts on the flap and pushes it sideways. Linkage transfers flap motion to the carburetor throttle lever, and the throttle is pushed closed, overcoming governor spring tension. As a result, engine speed is limited by governor action. Other engines use small flyweights in the crankcase to provide governor action. As speed increases, centrifugal force throws the small weights outward, and they push on a collar. Collar action is then transferred to the governor linkage. A small rod transfers this motion to the carburetor to close the throttle and limit engine speed. Although governor designs vary, they all use the same principles. An ignition system is needed to start combustion. The engine must produce a hot electric arc at the spark plug to start the mixture burning. Older ignitions use contact points and a condenser to trigger the coil to produce high voltage. As the magnets on the flywheel move past the coil, a magnetic field builds. When the points open, the magnetic field collapses and induces a high voltage onto the spark plug. Modern electronic ignition systems work in the same way, but an electronic ignition module replaces the contact points. The ignition module makes and breaks the windings in the coil to induce high voltage out to the spark plug. This is a cutaway of an actual ignition coil. It is bolted to the engine case so that it is close to the flywheel. Other designs, like this one, position the ignition coil inside the flywheel. In either design, as the flywheel rotates, the permanent magnets pass next to the coil. The magnets are often cast into an aluminum flywheel. As a flywheel magnet passes the coil, a magnetic field is induced around the coil primary. When the magnet moves away from the coil, the electronic circuit can sense the change in field strength and stops current in the coil primary. This causes the magnetic field to collapse across the secondary. High voltage then shoots out through the plug wire to the spark plug. An electric arc at the plug tip starts combustion on the engine's power stroke. The plug wire, also called secondary wire, has thick insulation to prevent shorting of the high voltage to ground. The spark plug threads into the cylinder head. The cylinder head is often a removable lid over the top of the engine cylinder. The head is held in place with special bolts or studs and nuts that thread into the cylinder block. With some two-stroke cycle engines, however, a removable head is not provided. The cylinder and head are cast together as one part. With four-stroke cycle engines, the head may also have to hold poppet valves. The valves slide open and closed in the valve guides in the head. When a valve closes, it contacts its valve seat to close off the port in the head or block. A head gasket seals the joint between the cylinder head and the block to prevent leakage. Some larger engines use intake and exhaust manifolds. They bolt to the outside of the head or cylinder block to carry gases into and from the engine combustion chamber. Gaskets and seals are also used on the crankcase cover to prevent leakage. Note the oil seal that seals the crankshaft snout. The crankcase cover provides a means of accessing the crankshaft, connecting rod, and other internal parts. The reciprocating assembly includes the crankshaft, connecting rod, piston, and piston rings. Since a piston reciprocates in the cylinder at tremendous speeds, it must be made light and strong. The piston is usually cast or forged of lightweight aluminum. A large hole is machined in the piston for a wrist pin. Grooves are also machined for the piston rings. The top compression ring must prevent blow-by or pressure leakage down the sides of the piston. When combustion pressure occurs, the compression rings must prevent pressure from blowing into the crankcase. Only used on four-stroke engines, the oil control ring must scrape off excess oil from the cylinder wall and keep it out of the combustion chamber. Called a scraper ring, the oil ring forces excess oil through a hole in the piston and back down into the crankcase. This cutaway shows the typical construction of a piston and rod assembly. Note how the piston pin joins the piston and connecting rod. Either a force fit or small snap rings keep the piston pin inside the piston. The large end of the connecting rod bolts around the crankshaft. The rod cap fits over the bottom end of the connecting rod body. Case-hardened bolts secure the rod cap. Connecting rods can be made of aluminum or steel. They must be very strong to withstand the tremendous downward thrust of combustion pressure on the piston head. With a crank and bottom of the rod spinning around in the crankcase, Oil is splashed on moving parts to lubricate and protect them from friction and wear. Mentioned briefly, a small gas engine valve train includes all the parts that open and close the valve seats or ports. The valve train must push each valve face off of its seat at just the right time in each of the strokes to cause flow in and out of the engine. In modern overhead valve engines, many of these components mount on the cylinder head. The valves, valve seats, valve guides, valve springs, seals, retainers, and valve locks all mount in an overhead valve cylinder head. With older valve and block engines, most valve train parts are in the cylinder block. Grooves are machined in the valve stems to accept valve locks. The locks fit into the stem grooves to prevent the valve washer or retainer and spring from sliding off the valve stems. Valve springs must rapidly push the valves and its related valve train parts to the closed position when needed. One end of the rocker arm contacts the valve stem. The other end engages the push rod. This animation shows the fundamental parts of an overhead valve train. The cam is a source of motion. It transfers movements to the lifter and push rod. The rocker arm then changes the direction of motion and pushes down on the valve to open it. Most rocker arms for small gas engines are made of stamped steel for lightness and strength. An adjustment nut and lock nut secure the rocker arm to its stud in the head. To keep oil spray in the engine, a valve or rocker cover and gasket bolt over the top of the head with an overhead valve design. The valve cover at the bottom of the picture is usually made of lightweight stamped steel. A gear on the crankshaft drives a larger gear on the camshaft to turn the cam at 1/2 crankshaft speed. Helical cut, crank, and cam gears are sometimes used for quiet operation. The lifters fit into small bores machined in the block, and the push rods extend up through the block and head to contact the rocker arms. In most small gas engine designs, the camshaft mounts in the crankcase next to the crankshaft. At low speeds, the rod on the mechanism touches the lifter to raise the exhaust valve partially off its seat and lower compression pressure for easier cranking. After the engine starts, flyweight action turns the rod so that it does not touch the lifter and the engine operates normally. To summarize the differences between 2- and 4-stroke cycle engines, a 2-stroke only requires 1 crankshaft revolution to produce a complete cycle, whereas a 4-stroke requires 2 complete crank revolutions to produce a power stroke. As a result, 2-stroke engines start more easily. A 2-stroke engine is a high RPM engine, while a 4-stroke engine produces good power at lower speeds. A 2-stroke engine is normally louder than a 4-stroke engine. 2-stroke engines are typically lighter and smaller than comparable 4-stroke engines, and a 2-stroke engine has fewer moving parts. However, a 2-stroke engine usually requires more maintenance than a 4-stroke. A fuel-oil mixture is used to lubricate and power the 2-stroke engine. With a 4-stroke engine, only oil is in the crankcase and only gasoline is burned in the combustion chamber. A 2-stroke engine runs hotter than a 4-stroke engine. A 2-stroke engine uses reed valves to control flow, whereas a 4-stroke engine uses poppet valves. A 2-stroke engine requires ports in the cylinder, which can reduce ring life. A 4-stroke engine has its ports in the top of the block or in the cylinder head. Besides 2- and 4-stroke cycle classifications already discussed, small gas engines can be categorized in many other ways. Cylinder arrangement refers to how the cylinders are oriented. The most common is the single-cylinder horizontal engine with a vertical crankshaft commonly found on lawnmowers. It has its crankshaft extending out the bottom of the block, ideal for spinning a cutter blade. The second most common is the single-cylinder vertical with a horizontal crankshaft. Its crank extends out the side of the crankcase, ideal for powering water pumps, snow blowers, and other similar applications. V or slant cylinder engines produce a lower profile engine, resulting in a more compact power plant. Small gas engines can be either air or liquid cooled. An air-cooled engine has large cooling fins formed on its cylinder and head to dissipate excess heat from combustion. The fins increase the surface area for improved heat transfer into the surrounding air. Fan blades formed on the flywheel push air over the cooling fins for rapid heat transfer. They are simple and inexpensive, but cannot control internal operating temperatures as well as a liquid-cooled engine. A liquid-cooled engine has internal water jackets formed around the cylinder and combustion chamber. A coolant solution of water and antifreeze is forced through these jackets by a water pump. A thermostat often controls flow and engine operating temperature. Liquid cooling is needed for high-performance engines because a liquid is more effective at removing excess heat. The type of lubrication system is another classification. Many small gas engines use splash oiling. A spoon on the lower end of the connecting rod simply dips into the sump oil at bottom dead center and splashes motor oil on moving parts as the crank and rod spin inside the engine. Pressure lubrication uses an engine-driven oil pump and internal oil passages for feeding motor oil to high friction points in the engine. The pump pulls the oil out of the sump through an oil filter and the rod bearings, main bearings, and the camshaft bearings. A pressure relief valve limits maximum oil pressure. Main and rod bearings can be classified as friction or anti-friction bearings. With friction bearings, two smooth bearing surfaces operate with a thin layer of oil between them. The bearing may be made as part of the rod or crankcase, or it may be an insert with a soft metal alloy outer layer on a steel backing. Oil grooves and an oil hole feed lubrication into the bearing clearance. With anti-friction bearings, either ball or needle bearings fit between the two spinning parts. Piston pins can be classified as press fit and floating. With a press fit pin, an interference fit is produced between the rod's small end and the piston pin. This holds the pin in place and keeps it from hitting the cylinder wall. With a floating pin, snap rings hold the pin inside the piston. The pin is free to float or move in the rod and piston. Most crankshafts are one piece, either cast or forged from iron and then machined to size. However, a few small gas engines use a built-up crankshaft which must be pressed together. Valve and camshaft locations are another method of identifying a small gas engine. Early engine designs position the camshaft and valves in the block, termed an L-head or flathead engine. The head was simply a lid over the cylinder and did not hold other parts. Newer engines tend to be I-head engines, which locate the valves in the head and the cam in the block. This configuration is also termed overhead valve. This design improves engine power and efficiency because the intake and exhaust ports can be designed for better engine breathing. High-performance motorcycle engines are often overhead camshaft designs with the cams and valves in the head for less valve train weight and higher RPM capability. Fuel type refers to whether the engine burns gasoline, diesel fuel, LP gas, or another alternate fuel like alcohol. Most small engines burn gasoline, and as explained, use a carburetor to meter and atomize the fuel into the air flowing into the combustion chamber. A few new engines use electronic fuel injection to more precisely meter gasoline into the intake ports. Diesel engines use a high-pressure pump to force thick diesel oil into injector nozzles. The spring-loaded injector nozzles spray a mist of diesel fuel directly into the combustion chamber when a high-pressure pulse of fuel enters the injector. With a diesel, The throttle control is linked to the governor, which controls engine idle and maximum speed. The governor then controls the injection pump. An LP gas fuel system usually meters liquefied petroleum gas into a conventional carburetor. Since many will operate on both gasoline or LP gas, they're termed a dual fuel system. A gas pressure control valve and other parts must be installed on the engine so that it can burn LP gas. The LP gas is desirable because it produces less exhaust emissions and less internal engine deposits. The type of starting system is also a way of classifying engines. Most small engines use a rope start mechanism. Pulling on the rope engages small fingers in the start mechanism to turn the crankshaft. When the rope is released, a spring releases the fingers and the rope is retracted back into the engine. With an electric start, a small battery, solenoid, and electric motor crank the engine. The battery is usually a lead-acid type that uses plates mounted in an acid solution to turn chemical energy into electrical energy. When the key is turned to start, a small battery current closes a solenoid. The solenoid then connects battery power directly to the starting motor. The motor then spins a small pinion gear that engages the larger flywheel ring gear to crank the engine. Now that you've learned how small gas engines are constructed and how they operate, you're ready to learn about diagnosis, service, and repair.